So we're going to talk today about hydraulic connectivity and what it is. A lot of this comes out of your text, but there's some supplemental stuff that's not in your text. Oh, and don't let me forget during the break to go over one-page summaries, because I think I got it all straight now, finally. All right. So we're going to be covering Darcy's equation today. So you need to be able to explain where his law came from, which is really just an observation of behavior. We're going to talk about hydraulic connectivity, and we're going to be distinguishing between the what we call hydraulic connectivity and what's the intrinsic hydraulic connectivity is. It's important. The intrinsic permeability, which is an important distinction because when you talk to certain engineers, there's a difference, and we want to make sure we have our language straight. I'm going to go over laboratory testing and common laboratory tests. I'll do that pretty quickly. But you need to understand the common laboratory tests and give descriptions of them. I think that's pretty much it. There's some more stuff. Oh, yes. Oh, God, I thought there was more. We're going to talk about Koseny-Carman, and I assigned a paper for you to read on Koseny-Carman as another way to get hydraulic connectivity from coarse-grained soils. And we're going to talk about it theoretically because I think it's a nice basis for understanding the soil structure and mechanics of soils that control hydraulic connectivity. And then finally, another paper I've assigned you to read is Mesri and Olson and Mesri, right? Which is a really nice paper on hydraulic connectivity of clay soils, because when it comes to clay soils, all that surface chemistry is going to be important, and it plays a big role in hydraulic connectivity of clay soils. So that's a really good paper, and that's one of the ones you're going to have to do a one-page summary on. And then finally, going to look at layered soil systems and talk about the average hydraulic connectivity, which will lead us to an understanding of why we always have a much higher horizontal hydraulic connectivity for natural soil deposits than vertically, or at least almost always. All right. So I always think that person on the right there looks like Professor Caduto's great-great-grandfather. So this is just one of my attention getters. So what do we know about Henri Darcy and Grey Poupon? They're both from Dijon in France. So this is back in the day when you were like when you were really just outstanding civil engineer. You could actually get the town plaza named after you. This is Place Darcy in Dijon France, and Darcy's a real famous guy in France because he brought a nice large quantity of fresh potable drinking water to town, a feat that is still important in many parts of the world. And this comes from, I like this quote. This isn't a quote at the beginning of Darcy's book, the treatise, Les Fontaines de Dijon, which is the fountains or the water supply system for Dijon. He's got this big treatise of it. But it's worth reading, especially looking at the date that this came out. I think we still underestimate the value of high quality water. In this country, we're worried about trace elements in water, whether it's chlorine or non-chlorine. But there's plenty of places in the world where we're still just worried about water that's just plain potable. And it's pretty amazing that we can do this, and it's really important. So I just think, all the way back to 1733, people were understanding how important quality water supply was. So this is the front page of Darcy's treatise, The Public Fountains of the City of Dijon. And that's one of his, there's a gal named Patricia Bobeck who did a really nice translation of it if you're ever interested. And you see right there one of the fountains at the end of his water distribution system, and you can look in the book and see the designs for that, and that's the way it looks today. It's still there, still running. Still doing its job. It'd be nice if our water distribution systems look so nice these days. So let's talk about Darcy's problem. So Darcy was trying to, Darcy knew that if you filtered sand, it took out most of the bad stuff and it tasted better, didn't make you sick and all kinds of stuff. So he was trying to understand how to design these filters. They'd basically just been designed using rules of thumb, and he was looking for a theoretical way to design these filters. So this is the basic problem. Water comes in the top of the comes in the top of the tank, it filters through the sand, it comes out the bottom. And the question he had was, well, I mean, how thick do we make the sand? How can I get the flow of water through that I need and do the proper refiltering? So while he was in recovering from being ill in a sanatorium, he did a bunch of experiments, and this is his apparatus. And it should look kind of familiar. So what do these things look like right here? Yeah, those are his manometers or piezometers, but they're not using mercury manometers for piezometers. And if you look here, you can see that this is his flow out. He's collecting the flow in this tank so that he can measure the Q by measuring the volume as a function of time. And then he's got the flow in is coming up this pipe, and he's got some kind of flow control here with a valve. So this is the basic parameters of his device. It's quite a tall tank. He had mercury manometers at the top and the bottom to act as piezometers. And the sand in the tank, he varied in different depths, and he put different kinds of sand in, but the sand was about 0.6 to 1.7 meters thick. And then he used this valve over on the left-hand side to control the flow. So he was controlling Q is what he was doing, and then measuring heads. He wasn't controlling head and measuring Q. He was controlling Q and then measuring the head. So this, if we idealize his experiment in this fashion, this is what it looks like. It's what we call a constant head test. In other words, the total head here at the top and the total head at the bottom are fixed at all times. So if we know the height of the top reservoir, we know the length of the sample, we know the height of the bottom reservoir, and we know the cross-sectional area of the sample, and then we can measure the Q flowing out. So that's how he set up his experiment. He was actually controlling Q and measuring H1 and H2, but either way, it's the same experiment. All right, and these are his results, which you can download online, look at, and all kinds of stuff. So he plotted the flow out as a function of the hydraulic gradient. Remember, if you recall from your fundamentals, the hydraulic gradient is the change in head divided by the length, so that's a dimensionless measure. And he did several tests. He plotted one set of data at different flow rates. And that looked like a straight line fit that one pretty well. And he plotted for a different test with a different sand. And he did a third one, and a fourth one, and he did a fifth one. And he said, looks pretty linear. So from this, he derived what we now call Darcy's law, which probably is better called Darcy's observation. So he noted that the flow out of the system was proportional to the change in head divided by the length, or the change in the gradient. And he didn't actually vary the area in this test, but it was done in other tests, and realized that the area was also proportional area. If you had twice as much area, you're going to get twice as much flow. So we commonly call that Darcy's law today, and we write it at Q equals KIA. So K is the constant of proportionality. So H over L is just I, A is A, and K is just the constant of proportionality. So it's the slope of that. It's the slope of this line. Right? So this is H over L, this is Q, so the slope of this line is K. So the gradient is H over L. So now K K is a function of both the soil properties and the fluid properties. If we've been running gasoline through this system, we would have had a different flow rate. You notice when Darcy used different sands, he got different flow rates and different proportionality constants. Now he only used water in this, but if we used a different fluid, we would have got a different answer too, because of the viscosity of the fluid. So it's important to understand that K is a function both of the soil and of the fluid. So for instance, it would be a function of the fluid temperature. If we ran water through there at different temperatures, we're going to get different proportionality constants. So the correct term for this constant is the coefficient of hydraulic conductivity, or sometimes just for short we call it the hydraulic conductivity because that's too many words. It is still often referred to, and in particularly in older literature, referred to the permeability, which is a title you should try and strike from your vocabulary when you're talking about this parameter, because there's another parameter which is known as the permeability, which is more accurate. Well, it's better known as permeability throughout more disciplines. We'll talk about that one in a second. But the key fluid properties we need to know are the viscosity and the mass density. If we know the viscosity and mass density, then we could take the fluid properties out of this parameter. And when we do that, we get a different parameter. And so we can write that the small k, the coefficient of hydraulic conductivity, is equal to a different constant times rho times the acceleration of gravity over the viscosity. And if we do that, the big K is known as the intrinsic or absolute permeability. And it's going to be a function of what then? Yeah, it's only a function of the porous media. And that's a really important number though. For instance, like, what's all the big news in petroleum production right now? Enhanced extraction techniques, right? And that entails things like fracking, which opens up the pores in the fluid, or injecting steam in, and all kinds of things that affect. So a lot of the enhanced extraction techniques have to do with heating the ground, and the issue is you're actually heating the petroleum, which changes its viscosity because it's a function of temperature. Or sometimes putting solvents in there or surfactants in to change the properties of the petroleum, and it's going to flow different. So when you talk to petroleum engineers, when they talk about permeability, they're talking about big K, which is the intrinsic permeability, which is a function of the material of the matrix. So fracking, for instance, changes big K. Maybe not fracture. Pumping steam into the ground doesn't change big K, it changes little k though, because it's changing the viscosity of the material. So we should call this thing hydraulic conductivity. I'm careful to do that, but you'll find it in lots of previous writings, particularly some of the papers I'm going to actually read, because some of them are several decades old. You'll see it referred to as a permeability. So just make sure you understand the difference between the intrinsic permeability and the hydraulic conductivity. Ours includes all those things. So if you're doing geoenvironmental stuff and you're trying to pump gasoline out of the ground that came from a leaking storage tank, you're going to have to deal with the fact that the stuff that you're trying to move through the soil is not water. But most of the time we're dealing with water. All right. So let's talk about velocities, because this can be confusing. So we can write that Q equals KIA, and I can divide both sides by A. So if I divide both sides by A, I get that Q over A is KI, and then Q over A is going to have what units? It's got linked over time, so it's going to have the units of velocity. So we generally call this the apparent velocity. It's called the apparent velocity or the Darcian flux, because it's really not the water is not traveling at VA, but the flux through the system is. So the water is only traveling through the pores. So it actually has to move faster than VA in order for that flux to be equal to VA. So that flux is really just, it's an apparent velocity. It's as if the water was flowing through the entire volume of the soil, Because that's just the way that Darcy calculated. If he wanted to, he could have calculated the porosity and calculated the void volume and divided by the apparent void area, but that's not the way we did the problem because it's hard to do. So we have something else called the seepage velocity. So the seepage velocity is the time, the seepage velocity, let me go back to my Darcy's picture here because it's a little easier to show. So the Darcian flux is, if I just calculate, this is the area I have, if I take Q and divide it by the area, that's the amount of water that passes through the permeameter at for any given time. Now, water's is not flowing through this entire area. It's only flowing through that area divided by the porosity is equal actually the area of flow. Oops. Right? So if I've got Q over A, water flowing through there over any period of time, but it's only flowing through some area that's less than the total cross-sectional area, the water itself has to be traveling faster than that to get from the top of here to the bottom of there in the same amount of time. So that speed that the water is actually traveling through the system right here is the seepage velocity, Vs. Oops. So Vs is just going to be equal to the apparent velocity divided by the porosity. Since that's the porosity is the void, the porosity is the volume of voids over the total volume. So that the seepage velocity divided by the porosity accounts for the fact that the water can only flow through the pores. So that's going to be a number greater than the Darcian velocity. So if you want to know how much water is flowing through a certain part of the system, you want to know the Darcian velocity. If you want to know how long it takes a molecule of water to get from point A to point B, you want to know the seepage velocity. Neither one of those is actually how fast the water is actually traveling, because the water doesn't take a straight path. As the water travels through the soil, it doesn't travel in this straight line. The water is zipping around all the particles and going back and forth. So its actual travel distance from the top to bottom is even greater than the length. So the actual water velocity at any given time is even higher than the seepage velocity. Is this making sense? Yes. Okay, good. So we have three velocities that we really need to worry about. We've got the apparent velocity, which is the flux. We've got the seepage velocity, which is how long it takes a molecule of water to get from point A to point B. And then we have the true velocity, which is how fast the water molecules are actually moving. The true velocity is not very important to us except in some geoenvironmental and chemical. So if you're worried about chemistry and you're worried about contact time, for instance, the true velocity can be important for stripping hydrocarbons off of clays and stuff like that. So there's a few places where the true velocity is important, but the two that we're really normally concerned about is the apparent velocity or the flux. That tells us the total quantity of water flowing through a given area. Or the seepage velocity, because I want to know how long it's going to take the ethyl methyl death that the guy across the street dumped in his backyard over to my well on my side of the property. So those are the two that we're most concerned about. And the true velocity is always greater than the apparent, is always greater than the seepage velocity, which is always always greater than the apparent velocity. All right, so let's talk about what controls hydraulic conductivity. So what properties will affect the K? Now, K is a function of what? Little k, hydraulic conductivity is a function of soil properties and fluid properties. So what properties are going to affect K?
Texture of the soil.
The what about the soil?
Texture of the soil, the size.
Okay, the size of the voids and the shape of the shape of the voids too, because the water's got to flow through it. So just like a rough pipe, you know, if you have a smooth pipe versus a rough pipe. So like the void ratio or the porosity is going to affect it, but not only that, the shape of the flow channels, and that's going to be a function of the shape of the particle. So particle shape is going to be important. Right, so those are the main ones. And then on the fluid side, we already know it's important. So the void ratio of the porosity is one of the important parameters. The void size, which is related to both. I mean, we looked at different soil structure, right? And for we already noted that for the same relative density, you can have different size voids. So it's not just the void ratio of the porosity, but it's also the size of the voids. And that's going to depend on soil structure. And then the void shape, which is going to be related to the particle shape. So there are some early works where we tried to correlate these things. And Hazen, I think most of you are familiar with Hazen's equation. So Hazen, again working in sand filters, trying to understand how to estimate hydraulic conductivity for sand filters, came up with a very simple equation that if you take the d10 squared, multiply by some constant, you're going to get K in centimeters per second squared. Most people take that constant to be 1, because it's a nice number and it's pretty close to between 0.8 and 0.1. So the d10 squared, where d10 is in millimeters, I believe. I think this is for d10 in millimeters. It's in your textbooks, so yeah, it's in millimeters. Now this was derived, again, for looking at sands. So this sands for filters. So these are sands that are relatively loose, because we don't really compact filters very well. And for sands of a size that you get a reasonable amount of flow. So it was limited to a certain range of sands. In the 1930s, Casagrande tried to come up with a empirical fit that included the void ratio, because obviously for the same material, if you change the void ratio, it's going to make a difference. So Casagrande's equation was, if you calculate the void ratio, if you calculate the hydraulic conductivity at a void ratio of 0.85, then this equation seems to tell you how that hydraulic conductivity will change as you change the void ratio. You get it more dense or less dense. Well, those are nice, but those are all just empirical fits, and there's some newer ones out there. There's one by Massman that's just a power series fit that includes the percent clay, the percent sand, and the void ratio. So there's some other newer ones out there, but they're all just empirical fits. None of them really none of them really deals with well, what are the fundamental soil properties that are affecting hydraulic conductivity. But the theory, there's a theory that discusses that, and that's I would say Darcy Weisbach. That's the Koseny-Carman. So let's look at what's really going on. So in this case, I've turned my permeameter on its side just to draw things, and if I'm a molecule of water here, I'm actually going to be traveling, not straight across the permeameter here, and my travel distance is going to be what I'm going to call big L1, and it's going to be longer than just the distance L, which is the length of the flow, the length of the gross flow path, right? And then if I'm in soil 2, I'm going to have a more tortuous path. I got more zigzags because I got big flat particles, and so I'm going to have to travel a distance L2, and those are going to be different. So what I'm going to do is I'm going to take those two flow channels and I'm just going to stretch them out in a straight line so we can look at them. So, and in this case, L2 is going to be longer than L1. So that's part of what's going on. Part of what's going on is I'm not traveling in straight lines. So L2 is going to be greater than L1. That's going to be greater than L, which is the apparent flow length. So I want to define a pseudo gradient. So we know that the hydraulic gradient defined by Darcy is the change in head over the apparent flow length, L. So I'm going to define a pseudo gradient, which I'm going to call capital I, which is the change in head over the actual flow length that the particle travels through. Then the next question is, well, how am I going to model these channels? Because, you know, this thing's wrapping around through all kinds of soil particles and stuff. I got to find a way to model the channels. Now, the flow at the flow rates that we're talking about in soils is always laminar flow. So the simplest model I could have of the pores would be tubes, right? I could imagine in a very simple model that the pores are just tubes, right? In that case, we got laminar flow, and if you remember laminar flow, we get this parabolic velocity gradient in a laminar flow area. And if we look up if you go back to your fluids book and you look up the parameters for laminar flow in a pipe, you'll find that the laminar flow in a pipe is equal to 1/2 gamma over mu. These are the fluid properties right here, times I, which is that was my apparent head, my pseudo head gradient, my pseudo hydraulic gradient, times RH squared divided by A, and you may or may not remember, but RH is the hydraulic radius, right? It's the wetted, the area divided by the wetted perimeter. This firing some old synapses in the back of your mind that you had from fluids along the. We don't have to derive any of this. I'm just reminding you of what you used to know at one time. Okay, but that's straight from fluid mechanics. Okay, so that would be the true velocity we're talking about now, though, right? Because that includes both the issue of pores and the true path. So this is the true velocity. So the true velocity is then equal to this equation. Well, this is a nice model, but it's a pretty simple model, and no matter how we look at the soil, I realize, well, there's not really tubes in there. There's all these things that are interconnected and stuff. And if I kind of look back at my Plady model, where I've got, where I've got these, these might be clay particles where the things are pretty flat. Well, that particular model might look more like flow between two plates rather than flow through tubes, right? I mean, that would be another model for the pores, another very simple model for the pores. So, well, let's look at that model. And if I look at, if I go back to fluid mechanics in that one, again, I'm looking at laminar flow. This is the equation for laminar flow between two parallel plates. And that looks pretty familiar. What's the difference between this and the previous equation for laminar flow in a tube? This is 1/3, the other one was 1/2. Other than that, it's the same thing, right? And that also would be the true velocity that we're talking about. Again, not the seepage velocity, not the apparent, not the Darcian velocity. This is the true velocity. Well, if I look at these two things, I can write both of those equations as the true velocity is equal to the density of the fluid divided by the viscosity of the fluid times 1 over some constant times the hydraulic radius squared times this pseudo gradient. And what does that constant account for? What was the difference between my two sets of fluid? Well, the void shape, let's just say, right? Yeah, which is one with the void shape, which is controlled by the particle shape. Right, so that's just a shape factor, right? And that's a shape factor, and it varies between. I mean, those are about the extremes. It varies between 2 and 3. Well, that's pretty good. If we got something that in geotechniques, it only is 1 over 2 or 1 over 3. Hey, we're sitting pretty well, right? All right. So now let's talk about what the hydraulic radius is in these cases. So the hydraulic radius is, remember, it's defined as the area of flow divided by the wetted perimeter. So in soils, I could think of that as, well, that'd be the area of flow divided by the surface area, surrounding all the area of flow, right? So the surface area of my particles divided, if I take the volume of flow, if I want to do this in 3 dimensions instead of 2 dimensions, think about the volume of flow I have, and then the surface area all surrounding that flow. So that would be approximately equal to the wetted perimeter. So that would be the volume of the voids divided by the surface area of the solid material in the soil. Yeah, are you with me now? We're going to call this the wetted perimeter.
Is
Okay.
that the total area of the surface area?
Yeah, so the total surface area. So I have a sample of soil that I'm interested in. I have the total volume of that soil and the surface area of all the particles within that, right? Because the water's we're talking about saturated flow. I should say that we're talking about saturated flow. So the water's going to be in contact with the surface area of all the particles. So I'm missing the contact area where they touch and there's no flow. But all right, well, the volume of the voids is just the porosity times the total volume. And if we knew the specific surface, in other words, if I know the surface area based on, as a function of the volume, if I knew how much, for a given volume, if I knew what the surface area of the materials in there was, then I could calculate the area, the surface area then is just going to be the specific surface times the total volume. I got to figure out, the first one's easy, we know how to calculate, we know what porosity is. This one's a little harder. We got to figure out how to calculate this specific surface. But if I knew it, I'd be in good shape. So then I could say that the hydraulic radius then is really just going to be the volume of the voids divided by this specific surface. Well, and then the volume of the voids is going to be the porosity times the volume. So this is just going to be the porosity divided by the specific surface. So that's equation 4. I'm going to use this as my hydraulic radius. So now I'm going to take this guy and I'm just going to shove him right back into there. And now I've got this equation for my true velocity. This is still the true velocity. So now I have that the true velocity is equal to some fluid constants times a shape, 1 over a shape factor based on pore shape, times the porosity squared divided by this specific surface area squared. So I'm gonna pull the n out of there. So now I just have 2 constants here. One of them deals with the shape of the pores, and the other one deals with the specific surface. And what's the specific surface going to be a function of? How am I going to get a higher or lower specific surface? Grain size, right. The smaller the grains, the higher the surface. So that's really a function of the grain size. It's actually a function of the grain size distribution, right? Okay. So now I have that my true velocity is just my fluid parameters times the shape factor for pore shape times a specific surface factor that's going to be a function of my grain size distribution times this capital I, but that capital I is not the real hydraulic gradient. I want to get back to the real hydraulic gradient because I can't measure this other one. I don't really know the path length. So I was equal to delta H over L. Big I is equal to delta H over big L. And what's the difference between little l and big L?
Big L is the actual, little L is the
Yeah. Little l is the apparent flow path, and big L is the actual flow path. So so then big I is just equal to little I times L over L. And I'm going to define L over L to be this factor that I call the tortuosity factor. In other words, it's how tortuous the flow path is. So let's go back to that. It's just a lovely term, isn't it? Isn't that just a great term? So let's go back and look at our picture real quick. So flow path 1 here is much less tortuous than flow path 2. Right? They could have the same porosity. They could have the same particle. They could even have the same specific surface, although the flat one's probably got a higher specific surface. But L2 is just more tortuous. In other words, it takes more wiggling around to get from one end to the other in L2. So now if I could just calculate that tortuosity factor, I'd be in pretty good shape. So I'm going to combine, so now just big I is little I times 1 over t, and I'm going to put that all together, and now I have this equation for my true velocity. So my true velocity is just my water properties times three factors that describe the soil. One's the shape of the pores. One's the amount of surface area, the relative amount of surface area, and the third one is how tortuous the path is. And then and we know how to calculate porosity. All right, cool. Well, SV is kind of hard to measure. So I'm going to change SV from SV to SS, because we do have measures of the specific surface, which is the surface area divided by the volume of solids. And if we assume things are spheres or other shapes, we can calculate the specific surface of a given shape, right? And we have estimates for this specific surface. So that's actually a much easier number to estimate compared to the surface area per unit volume of the whole soil. Well, if I just take this specific surface for the whole volume, and I multiply by 1 minus the porosity, that's going to give me the specific surface. So I'd like to make that substitution in there. And then my equation looks like this. Because those are all things that I can measure now. All right. And finally, this is still the true velocity, but it's not the true velocity that I measure, it's the Darcian flux that I really want to measure. So I got to convert this true velocity back to the Darcian flux, but if you remember, the true velocity is going to be equal to the Darcian velocity divided by n. That's the Darcian velocity divided by n is the actual Seepage velocity, times the change, times big L over little l, which is just equal to the Darcian flux divided by the porosity times the tortuosity factor. So I'm going to make that little substitution back in there. And then I'm going to end up with this equation, finally, this equation for my Darcian velocity as a function of the soil properties. So now we have a nice, neat equation for the Darcian velocity as a function of the things that are going to be important in the soil. So it's going to be a function of the fluid properties. We know what those are. This is a shape function for the pores, and we know that only varies from 2 to 3, right? This is the specific surface. That's going to be a function of the size of the particles and the shape of the particles. And this is a tortuosity factor, which is going to be a function of the particle shape, the particle distribution, and the structure of the soil, and the porosity. Well, cool. Can we measure those things? Oh, yeah, one final note. You can, if you like to write stuff in terms of void ratio instead of porosity, you can use this equivalency. I'm not going to show you this is true. I did go and derive it a couple of years ago just to prove to myself that it was true. So lots of times you see this is called the Koseny-Carman equation. So lots of times you see it written in void ratio. Sometimes it's written in terms of porosity. Sometimes it's written in terms of void ratio. It doesn't matter. All right. So notice that those four parameters there are the intrinsic permeability. Those are a function of only the porous media, right? Those are not a function of the fluid. But the whole thing is, is little k, or coefficient of hydraulic conductivity. We plug gamma water and we plug the density and the viscosity of water in there, and we're going to get K. But if there was something else flowing there, we could plug in other pore fluid properties. So this tells us that K should be proportional to E cubed over 1 plus E cubed, 1 plus E for a given soil. Because a given soil is going to have a given, it's going to have a given pore shape. You know, it's going to have a given shape factor. It's going to have a given specific surface, and it's going to have a given tortuosity. So here are some plots. This figure came from a figure out of DOS of hydraulic conductivity for some different soils at different void ratios. And he's plotted them versus E cubed over 1 plus E cubed, that's this one. So these are all the same data. And this one's, the second one here is, so this one goes here. The second one, he's plotted them versus E squared over 1 plus E, and the third time just as E squared. And so you can see any one of those seems to fit the data as well as any other one. So it's perhaps inconclusive, but certainly there's evidence that doesn't refute that the hydraulic conductivity is proportional to the E cubed over 1 plus E. But it's clear that there's other equations that could fit that. And we've made a lot of simplifications in this model. But that's about how good it is if you want to think of it that way. Now, these are plots for Olson, from Olson 1961, and some of this stuff is discussed in Olson and Mesri that you're going to read. So these are plots of the hydraulic conductivity, K, as a function of the porosity, and I will point out that this is in semi-log space here. So what do you see here? First of all, what kind of soils are these for? These are for clay soils. Okay? So what's the relationship? This is porosity instead of void ratio. Well, what's the relationship between porosity for these and hydraulic conductivity? Or even more important, what other parameters are being changed in these different plots?
Concentration of the ions.
Yeah, so the pore fluid chemistry is changing, right? So it's particularly look at the plot on the right, you know, what seems to have the most effect in hydraulic conductivity? Is it the porosity? You know, what's changing the hydraulic conductivity the most in that one? There is a porosity effect, and it seems kind of a strange one, because at really low porosity, at a low porosity, if you increase the porosity, the hydraulic conductivity actually goes down. But the thing that's more important is the clay mineralogy and the pore fluid chemistry, right? Well, where's the clay mineralogy or the pore fluid chemistry in Koseny-Carman? There isn't any. This model doesn't include any of that chemistry. Remember, because what's going on is we change the chemistry, right? The double layer water boundaries are increasing, and that double layer water boundary and that attraction of the water to the clay particles is going to have a big effect on hydraulic conductivity. So the Koseny-Carman equation looks like it might work pretty well for coarse grain soils, but it doesn't look like it works for squat for fine grain soils. And this is from Mesri and Olson, which you're going to read. And this is an even more dramatic effect. So what do we see here? This is the hydraulic conductivity. Notice they call it coefficients of permeability. That was the discussion we had earlier. But this is the hydraulic conductivity in centimeters per second as a function of void ratio for one soil, for illite. And what's the other parameter that's changing? We're changing the void ratio. But what's the other change? Why do we have 4 lines there? The pore fluid's changing, right? And what has the biggest effect on the hydraulic conductivity for this soil? Is it the void ratio? No, it's the pore fluid. So when it comes to clays, we can't predict the behavior of the hydraulic conductivity based on Koseny-Carman because it doesn't include anything about chemistry and the surface chemistry. It's not in the equation. So this is the same figure for smectite. So for smectite, you can read bentonite, and you see a similar behavior. And interestingly, this is a real interesting one. So this is the hydraulic conductivity as a function of void ratio for 3 different soils in a certain concentration of water with sodium ion. And as you can guess, the bentonite's got the lowest hydraulic conductivity, the illite intermediate, and the kaolinite the highest. Here's the concentration of this. Here's the hydraulic conductivity as a function of void ratio for the same 3 soils, all in carbon tetrachloride or another non-polar fluid. They're all the same. Because we have a non-polar fluid, we've eliminated the double layer water issue because we're permeating these things with carbon tetrachloride or another non-polar. So we don't have the absorption of the fluid on the clay surfaces because it's a non-polar fluid. And so now the hydraulic conductivity is simply a function of the structure of the clay and the porosity of the clay. And notice that their hydraulic conductivity is a function of void ratio. They all collapse on top of each other. Now, I will point out that's still to a log scale. It's a semi-log scale. I'm sorry, it's a log-log scale. And log-log scales cover many, many sins. You know, when you take things and convert them down to log-log scale, you eliminate a lot of variability. So there's a lot more variability than might appear there, but that just shows you how important surface chemistry is to hydraulic conductivity of fine-grained soils. And pore chemistry. So in a lot of the geoenvironmental issues, clay liner behavior and stuff, that pore chemistry is really important, and it can dramatically change the hydraulic conductivity. Notice that if you'd had a bentonite, and let's pick one, a void ratio of 2, you thought you were going to get 10 to the minus 11, hydraulic conductivity 10 to the minus 11. Let's see, we come over here too. But it turns out your landfill is actually holding carbon tetrachloride instead of water. Your hydraulic conductivity is going to be 10 to the minus, 876, 5.5. It's a little bit lower than 10 to the minus 11. And this actually is a big issue for geosynthetic clay liners. All right. So, let's do a quick summary. So this equation for hydraulic conductivity, we can use to estimate the hydraulic conductivity of coarse-grained soils. And if you read, I've assigned Goodbye Hazen, Hello Koseny-Carman to you. It's a really easy paper to read, and it shows you how you can actually calculate the hydraulic conductivity for a soil. You can estimate these parameters through grain size distribution, and you can actually go out and estimate hydraulic conductivity for coarse-grained soils if you know the grain size distribution, and all you need to know is figure out how you get a compact and a void ratio you can do it. And it works as well as anything that we've got to estimate hydraulic conductivity from. Now we're not doing just a correlation with something. We're actually doing, actually measuring real properties. Doesn't work for clays. Why doesn't it work for clays? Because that equation does not capture this behavior. Can't capture that behavior because that equation doesn't have any chemistry in it. And chemistry is really important. Yeah?
That's the equation just for the sand, basically.
Right, so that equation is good for, it probably works down to silt size. But below silt size, the surface chemistry is going to start playing an important role. Okay. Next. All right, so let's look at how we do tests. No, let's take a break. Perfect time for a break. And we'll come back to how we do tests after the break.